So, why do we need external modulation? In on off keying, one problem with direct modulation is chirp. So, issues with direct modulation. Case of on off keying, chirp especially at high frequencies, and the second is you cannot generate advanced modulation formats. What we call as advanced modulation formats, which is not advanced as far as the wireless technology is concerned, but in optics they are still called advanced modulation formats, such as QPSK or 16 QAM or OFDM or any of these things. Of course, I'll strike OFDM out of this, because maybe you can do OFDM with direct modulation also, but in general high spectral efficiency systems, advanced modulation formats, they cannot be generated with direct modulation of lasers. So, you need to do external modulation. Mind you, having said this, if you were signaling, if your signaling requirements are only of the order of gigabits per second, and if you are happy with the bit rates corresponding to on off keyed, you would still prefer direct modulation, because that is the most cheapest and the most compact and most elegant way of modulation. Okay. But of course, you cannot, you have these limitations, and external modulation is done with what is called as an electro-optic modulator. This is the most common external modulator, commercially used in the laboratories, used in research labs. This is a material, and this is the most commonly used material, lithium niobate. Okay. This is an electro-optic material. An electro-optic material is something where if you apply voltage, the refractive index changes. Okay. So, refractive index changes with applied voltage, that is an electro-optic, that is electro-optic effect. So, this is electro-optic effect. We are not going into the details of electro-optic effect, we will use it only when is necessary, but you can imagine that the refractive index change is proportional to the voltage that you apply. There are small issues like polarizations should be matched and things like that. The change in refractive index produced is different for different polarizations and so on, right. But we are not getting into the details of electro-optic effect, but for as far as a system is concerned, let us say N is proportional to the voltage that we apply. Now, we know that a change in refractive index means a phase change. So, which means that when I apply a voltage, refractive index changes, so the phase changes. Okay. And the beauty is the electro-optic effect itself, you can say it is like an instantaneous, even though it is said instantaneous, nothing is instantaneous, there is some, it's instantaneous with respect to what is the question, right. So, here in electro-optic effect, what really happens is when you apply a voltage to the system, dielectric properties of the systems change. So, the chi changes, and which is the what is chi? Susceptibility changes, and because it is the atoms that are responding, they respond at time scales of 10 power minus 16 seconds, of the order of femtosecond is their response time. So, so long as your modulation is in gigahertz, you can say 10 power minus 16 is like instantaneous, right. But tomorrow if you are trying to do a modulation at 10 power 16 times a second, let us say there is electronics which is doing, then of course electro-optics effect will start having its own lag. But for now, for the kind of modulations that we are doing today, you can consider the response of electro-optic effect as instantaneous. Okay. And how does it work? Here we are just doing a system level understanding of electro-optic modulation. You take, this is the basic structure, okay, the schematic. So, what is shown in the blue is the lithium niobate substrate, it's all on a waveguide. Okay, on the substrate you make an optical waveguide so that light is trapped inside this waveguide. Okay, so this refractive index here is n is larger than, let me call this as NC, and this is n clad, NC greater than n clad, so that light is trapped in that waveguide. And on either side of the waveguide you put electrodes, typically silver electrodes or gold electrodes are put on that, on the waveguide. Okay. And as your input light, so this is continuous wave light which is not modulated light, right, is applied to this electro-optic modulator. Of course, you have to do some work to focus the light into the waveguide and so on. Light propagates through this waveguide, and when you apply a voltage on this electrodes, depending on the voltage that you apply, the phase experienced by the light is decided by the voltage. So, what comes out is modulated. Of course, this is phase modulated because all what you did was apply a voltage. When you apply a voltage, this voltage changes the phase, and if this voltage changes as a function of time, phase changes as a function of time. So, you get a modulation which is, whose phase is dependent on the voltage that you apply. Okay. So, this will be input from a laser, from our narrow line laser, okay, which will be operating at a certain center frequency, let us say omega c. As it passes through the waveguide, it accumulates propagation phase, there is an e power j beta z, but that is constant. What is time varying in the system is v as a function of t. So, the phase experience changes as a function of time, and so you get an output which is modulated. So, we write the cross section, this is how the cross section is going to look like. The structure is going, so this is the waveguide, I mean, so I am looking at this side view from the side. Okay. So, the waveguide is here, the light is trapped inside, the electrodes are on the side, these two electrodes are what is represented here, and you are applying a voltage to one of them, the other one let us say is grounded. Okay. So, it means that if you have a structure like this, the electric field, there is electric field from positive to negative. So, you have electric field like this. So, the light is experiencing the electric field, applied electric field, and so this light is experiencing a phase change because of the, so the refractive index of this region changes with the voltage here that you are applying as a function of time. Of course, if I am doing v of t, I should mark an AC here, and because this n is changing as a function of time, you have the phase phi of the light that is propagating through this waveguide change as a function of time. Okay. And I can write this mathematically like this: E out as a function of time is my E in e power j omega t, I am leaving it, j phi of t is just the accumulated phase. I have, remember, I am not specifically writing the propagation phase. There is of course a e power j beta z, I am not writing that. That is not changing with time, that is a fixed phase. So, to be correct, I should write E in e power j phi naught, which is the fixed phase, and e power j phi of t. Okay. This is the fixed phase accumulated. But on the time varying part is this, and I am writing this phi of t as pi v of t divided by v pi. Okay. This v pi is a constant which is characteristic of my device. V pi is a constant, it is a voltage required to induce a phase change of pi. When your V of t is 0, when your applied voltage is 0, what is E out? E in. When your V of t is equal to V pi, your output is e power j pi. So, I can say that V pi is a voltage that I need to apply at the input such that the phase at the output is pi. This V pi definition is required for the system definition of the electro-optic modulator. You need to quantify what is the relation between the applied voltage and the phase change. If you look at the device, it will depend on where you are keeping the electrode. Depending on where you are keeping the electrode, the electric field intensity experienced by the waveguide is different. Depending on the size of the waveguide, the overlap integral is different. Depending on the polarization, your n is different, right. There are so many device specific details which we are not going into. So, we are going to do only a system level description here, right. So, all what we are saying is that I give an input, I get an output, the voltage that I need to apply to produce a phase change of pi because of my applied voltage, not because of the propagation, right. That is my V pi, and that is characteristic of my device. So, if I want to do a phase modulation, all what I need to do is, let us say I want to do a phase modulation at a 25 gigabaud rate. How will I use this device? I will take this electro-optic phase modulator. This is what we are describing as a phase modulator. Okay. I take this phase modulator, it will come like this. I have this, I have a fiber in, fiber out, right. I will actually have a fiber here which is glued into the waveguide, right, and then I have an RF pin where I am applying my 10 or 25 gigabaud signal. What I will get at the, so I'll take my laser, connect it to the modulator, and this is my detector, and let us say this detector has the ability to detect phase, right. All what I need to do is to give this RF into the modulator VRF at 25 gigabaud. So, I signal my V of t at zeros and ones, right, 0 and 1. Question is, what is this voltage corresponding to 1? I should, if my modulation is between 0 and pi, my 1 would correspond to V pi. I should give a voltage corresponding to V pi, so that whenever the voltage is V pi, the output phase is pi, or I have a difference in pi between, I cannot say output phase is pi, phase is always a relative quantity. All what I can say is that when my voltage swings between 0 and V pi, my phase at the output will have a difference of pi, and that is how I can do a phase modulation. And because I said it is an instantaneous process, I do not have a problem because of the delay here. The only delay that I will have is the electrode themselves will have some capacitance. So, that is a transmission line. So, if you design the transmission line very carefully, you can avoid the delay because of the transmission line.